During our first meeting of the fall 2021 semester, we talked about the syllabus. We talked about the idea of checking your email several times a day on DTL. And we also said we were going to start looking at our first problem, which was solve f of x equals 0. There's three aspects to this that we'll have to think about. There's the logic of the methods, there's programming the methods, and then there are numerical experiments to be done as well. Moreover, we'll assume that the solutions that we're looking for have this nice property. At a place where the function is 0 in value, the derivative is not 0, so that the function cuts cleanly through the x-axis. Such a thing is called a simple root, and these are basically the nice ones. If you have a function whose value is 0 at a point, and you have a horizontal tangent line, this is going to cause us a lot of trouble at some point. Bisection is based on this fact. If the function of interest is continuous on the interval from a to b, and the function value at x equal a versus f at b have different signs, for instance, here I might have a positive function value, while here a negative, or conversely, at the left end I might have a negative function value, and at the right end a positive one. Since my function is continuous, I have to be able to draw the entire graph from A to B without picking my pen up, meaning there's at least one place between A and B where f of x is 0. If I have two x values where the function values are opposite in sign, they will always form what's called a bracket of the root. Suppose, for concreteness' sake, that the function value at a was positive, while at b it was negative. Select some point in the interior and look at its function value. Momentarily discounting the possibility that we've accidentally landed right on a spot where f of x is 0, then either f at this new point is positive or it's negative. If it's the first case, if f is positive, then the function value is positive here but negative there, and I am guaranteed that there's a root within this smaller subinterval. If this isn't true, then the function value would be negative. Function value here is positive. That would tell me that there's a root in this smaller subinterval. Our strategy is going to be to pick some representative point close to the middle, or maybe the actual midpoint, look at its function value, and decide, do I keep this half or do I keep that half? So starting with an appropriate A and B, calculate the midpoint. We'll have to talk about some details later. If f of m and f of b have opposite signs, then there's a root between m and b. I'll set my left end of my interval to m, which makes my new interval the midpoint of the old one up to the end of the old one. If that's not the case, then I'll lower the b to the midpoint value. This is the end of the if then else clause. If A and B are very close together, then I will declare victory and say that I found the root. If that's not the case, I'll just go around in a loop and do all of this procedure once again until the interval is small enough to make me happy. As a concrete example, let f of x be x cubed minus 15. This is a simple problem which we can easily find the exact solution of. We're going to use it as a test bed for our bisection idea. I'm going to start with a equal 1 and b equal 3. F of 1 is 1 cubed minus 15, negative 14. F of 3 is 3 cubed minus 15, which is 12. Negative at one end, positive at the other. So the interval from 1 to 3 is a satisfactory initial A and B set. Find the middle, average the x values at the end. 1 plus 3 over 2 is 2. That's the middle. F of 2 is 2 cubed minus 15, which is negative 7. I don't really care about the precise value, I just care about the positive or negative part. 1 had negative function value, 3 had positive function value, and 2 worked out to have a negative function value. This tells me that I am guaranteed to have a root between 2 and 3. There may or may not be a root between 1 and 2. The intermediate value theorem doesn't tell me enough to say anything. Since I know there's a root between 2 and 3, calculate the middle of that interval, which is x equals 2.5 for the midpoint m. F of m is 2.5 cubed minus 15, which is 0.625, which is positive. Negative and positive at the ends, and positive in the middle. This time, negative here, positive here, tells me that there's a root between x equals 2 and x equals 2.5. The intermediate value theorem says nothing about what goes on between 2.5 and 3. So we throw this part away and keep 2 and 2.5. Do it again. Average 2.25 and 2.5 to get 2.375. The function value there is negative. I didn't bother writing all the digits down. It's the negative that is important to me. Negative here, positive here, negative in the middle. There is a root of my function between 2.375 and 2.5. This is somewhat tiresome, but when you have a computer to do it for you, it will be much less so. Average 2.375 and 2.5 to get 2.4375. The function value there is negative 0.517 and other digits. Negative, positive, negative. There is a solution to my equation between 2.4375 and 2.5. And then do it again. By this time, the details should be obvious. The latest estimate of our solution is 2.46875. I want to compare that against the true solution of the equation, which actually is easy enough to figure out. X cubed minus 15 is 0. X cubed is 15. X is the cube root of 15. 15 raised to the 1/3 power, which according to my calculator is 2.466212074. If you look at my latest estimate from bisection, I have the 2, I have the 4, and I have that first 6. I've got 3 significant figures correct. I hope this has been helpful. I'll see you in our next meeting. Everyone, have a great day.